Okay, so describe the relationship between the wavelength of visible light and its relative energy. Well, we know that visible light is the spectrum of electromagnetic radiation, also known as light, that our eyes can actually pinpoint and we can actually detect, right? So we can actually see this type of electromagnetic radiation. And we know that light is made up of photons, right? So a photon is a quantum or discrete unit of light, right? And we know that some of the colors associated with visible light, or some of the wavelengths of light, include red, orange, yellow, green, blue, indigo, and violet, right? And the reason we use this mnemonic, the reason we orient the colors in this format is because as we go this way, right, red is the highest wavelength. I'm going to use lambda for wavelength. And as we go this way, violet is the lowest wavelength. Now, according to some of the equations that we looked at, specifically Planck's constant, where the energy of a photon is equal to Planck's constant, Planck's equation, is equal to Planck's constant times the frequency, and we know that light is a transverse wave. So because light is a transverse wave, we can use the wave equation, and we stated that the wave equation was v is equal to f lambda, right? And we know that the speed of light in a vacuum is equal to c, and c is equal to 3.0 times 10 to the power 8 meters per second. So we can tweak this equation and we can solve for the frequency, which is the speed of a wave over wavelength, which is c over the wavelength, right? Whoops. It's just c over the wavelength. And if we take this notion and we plug it into Planck's equation, we plug this into Planck's equation, the energy of the photon is equal to h times c over lambda. Okay, so using this equation, we can see that as the wavelength increases, the energy of the photon decreases, and vice versa. That is, as the wavelength decreases, the energy of the photon increases. Okay, so, and the relationship between this, we understand that as the wavelength gets larger, and we know wavelength is the distance of a cycle, right? So if we have two waves, such as one like this and the other guy like this, right, the wavelength for, let's call this guy wave 1, right, the wavelength of wave 1 versus the wavelength, and this is wave 2, right, we can see that wave 1 is, the wavelength is greater than wave 2, so as a result, we can see that wave 1 is a slower moving wave than wave 2, right, so this guy actually has a higher kinetic energy. As a result, the energy of the photon is higher, and this guy actually has a lower kinetic energy, right? So basically, if we have a larger wavelength, that means that the wave is moving slower. If we have a smaller wavelength, the wave is moving faster, because of the fact that the larger wavelength wave is going to take longer to complete a cycle, right? So this is really the analogy, right? So you can also think about energy of photon related to its speed of a wave, right? So as the wave speed increases, the energy of the photon also increases, and we understand that as the wavelength increases, the wave speed will decrease. So as a result, the energy of the photon decreases. Okay, so that's basically the explanation of why red has the highest wavelength and lowest energy. So using this description, I'm going to say that red has the lowest energy, and violet has the lowest wavelength and highest energy. It's an inverse relationship. Okay, so that's the relationship between wavelength of visible light and its relative energy. Okay, let's explain Bohr's hydrogen emission spectra experiment and some of the conclusions and their inferences to the atomic structure. So recall that for Bohr's hydrogen emission spectra experiment, what he did here was he took a cathode tube. So let's say this is the cathode tube, right? He filled this cathode tube with hydrogen gas. Okay, so this cathode tube was attached to some kind of voltage source, creating the electrical current. and there was basically hydrogen gas on the inside of the cathode tube. Now this is originally colorless. What he did was he ran an electrical current through it. So there was an electrical current that was being surged through this, and what he found here was that the cathode tube actually started to glow red. Okay, so the cathode tube started glowing, so the gas actually started glowing. And he wanted to explain what was going on, right? What was happening, basically, right? So, and he also found that as he increased the current, right? So as he got the cathode tube here, and he increased the current. Okay, so let's say that this is an increase in the current, right? There was a shift in the color from a red shift to more of an orange shift. So there's a reddish orange shift here. Okay, so how he explained this, he used the model where he governed the position of hydrogen, which has basically 1 proton, 0 neutrons, 1 electron, right? He basically he looked at the position of the electron in these levels, and he called them energy levels, right? So Bohr stated that ground state of an electron was the electron at its lowest energy level. Okay, so how he looked at these energy levels, I'm just going to use these lines, right? And when you use energy levels, we're going to use energy levels as n. Okay, so n is the energy levels, and what Bohr initially thought of as at the lowest state of the atom, the atom was on its first energy level. Okay, so I'm using n for the energy levels 1, 2, and 3, right? So this is ground state of the atom. Okay, so this is the ground state of the atom, and basically what happened was when the electron gained energy from the voltage source, the electricity, right? When the electron gained energy, right, what happened was it jumped, right? It actually jumped from one energy level to its lowest energy level state to a higher energy level. So now it jumps to the second energy level. So now the electron is located here. Okay, so it's jumped from the first energy level to the second energy level. And at its higher energy level, Bohr stated that this constituted the electron's excited state. So the excited state is the higher energy electron. Okay, so the ground state is the lowest energy electron, right, before the energy was added, and then the excited state, it's the electron's higher energy state, right? So when we're looking at energy, we can also think about this just in terms of kinetic energy. So there's more movement, which also constitutes reactivity, right? The electron is more reactive. So now the electron's at an excited state, but it doesn't stay there forever, right? So these jumps from the lower energy level to higher energy level, Bohr called these jumps transient jumps. Okay, these electrons undergo transient jumps, and a transient jump is a temporary jump. So the electron doesn't stay at the excited state energy level for too long. It basically it falls back to its ground state, right? So then the electron basically will fall back to its ground state, and when it falls back to its ground state, the electron actually releases the energy that it absorbed, right? So you can understand that the electrical energy that the electron absorbed, it actually gets released in a certain number of photons, right? And the photons have a specific wavelength and frequency. Okay, so what gets released here is a series of photons, and we actually see the red wavelength. So photons with the wavelength that constitutes red light, right? So we see it as red light because these are photons with this particular wavelength and frequency that's consistent with the red portion of the visible light spectrum, right? So these are basically the energies now released as photons, okay? And what Bohr saw was that in the case where he increased the electricity, increased the voltage, now what happened was, using the same model, instead of the electron jumping into the second energy level from ground state, it actually jumps to the third energy level, right? So now it actually ends up here, right? And now because it jumps to a higher energy level, it basically falls back down from a higher energy level. So it falls back, instead of from the second energy level to the first, it falls back from the third energy level back to the first. And as a result, this time it releases orange wavelength of light, right? And we know that according to the visible light spectrum, right, it's photons with the orange wavelength. Oh, sorry. The orange wavelength of light. And according to the visible light spectrum, red has the highest wavelength, the lowest energy, and violet has the lowest wavelength but highest energy. Orange actually has more energy than red, right? So Bohr stated that as you increase the amount of energy that the electron can absorb, you'd have different spectral colors being released. Specifically, there would be a shift this way in the visible light spectrum. So this told Bohr, this basically inferred to Bohr that there was basically an infinite number of energy levels in an atom, right? So I'm going to indicate that here, but some of Bohr's conclusions stated that there were an infinite number of energy levels in an atom, and he stated that the energy levels describe the orbit of electrons around the positive nucleus. So this effectively created his planetary model, right? Bohr's planetary model, where the nucleus was in the center and the electrons, so this is the nucleus was in the center, and the nucleus consisted of the nucleons, the protons, and the neutrons, and the nucleus was in the center, and the electrons would orbit around the nucleus in energy levels that he called electron shells, right? So he basically called these guys electron shells, and Bohr stated that there was an infinite number of electron shells, which represent an infinite number of orbits that you can basically have in an atom, right? But one of the other big conclusions that Bohr stated here was that the energy of an electron is dependent on its position from the nucleus, right? So the distance of the nucleus would determine the energy of an electron, right? And as a result, electrons in the same shell should have the same energy, and vice versa. Right, so this basically indicated that electrons in the same shell were the same distance away from the nucleus, and as a result they should have the same energy. And this basically refers to the relationship between the attraction of the nucleus to the electron. If we use Fe to represent the force of attraction, force of electrostatic attraction, between the nucleus and the electron, then we can understand that the force of attraction is dependent on distance, right? I'm going to use r as my separation distance, right? We understand that as a separation distance, I'm going to use r, not lambda. As the separation distance increases, then the force of electrostatic attraction decreases. And we also know that the force of electrostatic attraction affects the kinetic energy of an electron. Right? So if the force of electrostatic attraction decreases, then the kinetic energy of an electron will increase, and vice versa, right? So the more force of attraction that there is from the nucleus to an electron, the more limited the electron's kinetic energy is, right? And if the separation distance decreases, the force of attraction increases, and as a result, the kinetic energy of an electron decreases, right? So using this notion, Bohr created his planetary model, and this was really instrumental in understanding chemistry, especially reactivity, within the turn of the century. However, this method has limitations, and now we utilize, instead of using the Bohr-Rutherford model that Bohr created, we basically will use the quantum mechanical model, because he did not look at energy levels in between shells called subshells. So we'll talk about that. All right, let's describe some of the limitations of Bohr-Rutherford atomic structure. Right, so according to Bohr's atomic structure, right, we usually credit Bohr with putting this model together. His planetary model, he basically stated that the electrons orbited around the nucleus, and the nucleus consisted of the protons and neutrons, also called the nucleons, right? So here is an example of what Bohr-Rutherford structure would look like, and I'm going to use fluorine to describe it, right? So I'm basically expressing fluorine as an atomic number of Z, atomic mass of A, right? And in this case, fluorine has 9 protons. Because we're looking at elemental fluorine, 9 electrons and 10 neutrons, and these two should add up to an atomic mass of 19 atomic mass units, right? So if I'm looking at fluorine, if I'm drawing Bohr-Rutherford atomic structure, you'd have 9 protons in the nucleus, 10 neutrons in the nucleus, and then the electrons would orbit around the nucleus in shells. So I'm going to draw these shells. Bohr looked at these shells in circular orbits, right? Perfectly circular orbits. Now he did note that this was 3 dimensions, so this would have been a sphere, right? However, we know that the orbits actually aren't circular, they're more elliptical, right? So the distance between each segment of the circle is not the radius to the center, right? So that's also another flaw in his model. Now, the electrons were oriented in these energy levels called shells. So this is the first energy shell, n is equal to 1. This is the second energy shell, and then this is the third energy shell, and it'll just keep going till n approaches infinity. There's an infinite number of energy shells. However, we're not really focused on energy shells that don't have electrons. We only look at energy shells or energy levels that have electrons. These energy shells, once again, demonstrate the orbits of electrons around the nucleus. Now, there's 2 electrons in the first shell. We know that the first shell can hold a maximum of 2 electrons. The second shell can hold a max of 8 electrons. And for the first 20 elements, we can assume that all other shells will hold a max of 8 electrons. Right? However, in the third shell, the actual maximum is 18 electrons. We'll explain this more when we look at the current model that we use for atomic structure, which is the quantum mechanical model. Anyways, looking at Bohr-Rutherford model, this indicates that there should be 6 electrons in the second shell. Okay, so there's 6 electrons in the second shell. There's 7 electrons in the second shell, right, as shown here. And Bohr stated that depending on the position or the distance of electrons from the nucleus, let's call this a radius, and this is the first shell, we'll call this R1 as the separation distance for the first energy level. We can see that these two electrons are the same distance from the nucleus, right? So if we call this guy electron 1, electron 2, and then we call this electron 3, 4, 5, 6, 7, 8, and 9, right? The energy level of electron 1 should be equal to the energy level of electron 2, as the separation distance of electron 1 is equal to the separation distance of electron 2. Okay, so I'm using R as the separation distance, right? And we should also, according to Bohr's model, the energy level of electron 3 should be equal to the energy level of electron 4, equal to the energy level of electron 5, and so forth, all the way to electron 9, because the separation distance of electron 3 is equal to the separation distance of electron 4, which is equal to the separation distance of electron 5, right? We understand that as the separation distance increases, the force of attraction between the nucleus and the electrons will decrease, and as a result, the kinetic energy, I'll use K for kinetic energy, the kinetic energy of an electron will increase, right? And vice versa. So if you have the same separation distance, you should have the same energy. However, this statement for all the electrons in the second energy level was not true. And the reason it wasn't true was because Bohr did not look at the presence of subshells, right? So there were actually energy levels existed between shells. That there were actually energy levels within shells, right? So the reason Bohr did not pick up on this is because Bohr did all of his experiments. Most of his experiments with a monoelectronic model. A monoelectronic model means basically an atom that only has one electron. So he only did most of his experiments with hydrogen, right? So you can use hydrogen to explain polyelectronic systems. Does not explain atoms with multiple electrons, right? Atoms with multiple electrons are going to have different types of electron interactions, right? So this is one of the reasons why he didn't actually look at, or he didn't actually notice that there were these energy levels within shells, and these were called subshells, right? So he did not discuss the presence of subshells, right? Once again, Bohr's model also assumed circular orbits, right? So Bohr's model also assumed circular orbits, where in actuality the orbits were more elliptical, right? So if you have a circular orbit, then from any point of the circumference or the outside of the circle to the center, you should have a radius. However, that's not completely true, right? So that's another reason why Bohr's model didn't really work too well, right? So because of both of these things, Bohr's model couldn't explain the energy level between different different atomic elements, right? So we needed to create a new model where the position of an electron was more pronounced in describing the energy of itself, right? So this is where we're going to kind of discuss the creation of the quantum mechanical model of the atom.